Hello everyone, my name is T and I'll be presenting my independent project which is a cable-driven elbow rehab exoskeleton. As most of you have already known, neurological and musculoskeletal diseases such as strokes, Parkinson's disease, and spinal cord injury are common causes of disability. Data shows that the number of old people increases every year and the rate at which occupational traffic and other accidents occur is also high. Patients of these diseases lose strength, sensations, and functions of their limbs, preventing them from doing activities of daily living. Traditional physical therapy makes use of neuroplasticity through repetitive exercises. Nevertheless, traditional therapist treatments still have some drawbacks, including high cost, long treatment duration, long recovery time for patients, and exposing therapists to fatigue and strain. For midterm 2, I made a 5-finger glove for hand impairment rehab. In this project, I proposed a portable elbow exoskeleton that can be used both at home and outdoors. While I was doing literature research, I came across some devices that are end effector based, like the MIT Manus in Motion Arm 2 and the Arm Guide, or devices that are hybrid, like the Armin 2 and the Arm Exoskeleton. My design is of exoskeleton based type. Current exoskeleton utilize different actuation strategies. Electric actuation, including cable actuation and gear actuation, are the most used method. Pneumatic actuations are also commonly used. The activation method I'm using in my device is cable-driven actuation. I noticed that there are various control strategies, including EMG signals, joint angles, and forces. For forces as control inputs, most of the previous works used a different kind of force sensors. I only found one work that uses the force-sensitive resistor for control, which I am also using for my prototype. When designing the exoskeleton, I separated approaches into different aims. My first aim would be to design a wearable and portable device. My second aim would be to actuate the system with a stepper motor and cables. And my last aim would be to control the device with force inputs. In all three aims, safety is also considered. So into the first aim, ideally, the overall device would be placed in a backpack with the circuitry inside so that the device can be portable. For the exoskeleton, it is comprised of 3 bands made of low-stretch fabric stick together by Velcro. Each of the 3 bands would be worn on the forearm, bicep, and shoulder respectively. A cardboard, which is used to support the stepper motor, is placed on the shoulder band. As you might know, an elbow has 2 degrees of freedom: flexion, extension, and pronation, supination. Cable actuation allows the exoskeleton to address the degree of freedom associated with the flexion and extension. The circuit includes a power supply used to power the stepper motor. The stepper motor is linked to a driver board which is connected to the Arduino Uno. There is also a force-sensitive resistor which is placed in a voltage divider. I soldered the force sensor to wires so that the user does not have to be too close to the breadboard to control the system. The current wires are about 4 inches long. In the future, it would be better to get 20 inches long wires so that the user can hold the force sensor on their hand. By employing the force sensor in the circuit, forces are used as control inputs. In the code, I specified a force threshold, and when the applied force on the sensor reaches the threshold, the motor shaft will rotate clockwise for 5 rotations and stop for 5 seconds and rotate counterclockwise. This video is played at double speed. And then finally, this is the working prototype. When the stepper motor winds the cable, it lifts the elbow up, making a 90-degree angle between the forearm and the bicep. After stopping for 5 seconds, it lowers the elbow down by unwinding the cable. Usually, for all of my projects, I would ask my brother to use the devices. However, for this project, the stepper motor is not strong enough to pull his elbow since it's very heavy. That's why previously I had my sister who has a lightweight elbow to use the device instead. So one modification I would make is to switch to the Adafruit NEMA 17 stepper motor, which can pull 8 times stronger than the current one and is about $10 more expensive. Two modifications I would make are to attach a flex sensor to the bottom of the elbow and to use EMG signals as control input. The flex sensor is used to determine if the elbow is bending enough and if it is bending like how a normal elbow would bend. For the EMG signals, I want to use intention-based control because it would be more beneficial in later stage of rehab than trajectory-based control. The far right picture is how I'm planning on attaching the sensor, and here's the table comparing the weight and cost before and after the improvements.